All right, so now let's talk about a theorem of Gauss, or Gauss's law, and it relates the divergence to the volume integral of the divergence to the area integral of the outward surface flux. All right, so let's do that calculation. All right, so if I want to do Gauss's law, so Gauss's law, or the theorem of Gauss, I guess. The theorem of Gauss. And I imagine I have a volume, so some volume. It doesn't have to be rectangular, it could be any old shape. Shape is arbitrary. And I imagine dividing it up into little cubes. Cubes, all these little cubes. And what we know is that the divergence is the outward flux per unit volume. So every little volume is going to have, the divergence will be the outward flux through this little cube. And if I have two neighboring cubes, right, two cubes one beside each other, well, my picture's not very good. When I do the area integral, or of the outward flux, when I integrate the outward flux through the surface of this one, I get a contribution from the midface between the two cubes, and what is outward of this one is equal and opposite what is outward of this one, right? So the interfaces between each of the boxes are going to cancel pairwise. And so if I take a big cube like this one, then all the interior interfaces are all going to cancel, and all I'll be left with is the outward surface flux of the bigger surface. And that's basically the theorem of Gauss. It says that the area integral, and I'll call through the surface of a volume of V dotted with ds is equal to the volume integral. So this is the surface of the volume, and this is the actual volume of the divergence of V. So in other words, if you integrate over the whole volume the divergence, all you get is the flux out through the surface. So as an example, if you picked a patch in the ocean, and V here was the mass flux, then since there's no net mass produced anywhere in the ocean, mass is conserved, then the divergence of V, where V is the mass flux, would be zero, right? So at any point, there can be no mass created. And so the outward, or you can see it this way, the outward flux of mass has to integrate to zero. In other words, what comes in must come out, right? And so this here is a theorem of Gauss. And this turns out to be very useful, and we'll use it all the time. So remember, if you integrate the divergence over a volume, that will be equal to the surface integral of the outward flux of V. So the only way the outward flux will integrate to something that is not zero is if there are interior sources or sinks. If you have an interior sink, for example, then there can be a divergence somewhere as the flow flows in, and since stuff will have to come in through the sides to flow out the sink. And vice versa, if you had a source in the inside, then there could be an outward flow out through the sides. So if you were doing an atmospheric pollution example, right, you have a smokestack, and there's smoke billowing out, and you make a little control volume around your smokestack, right? And in this case, the pollution that comes out through the side of the box is going to be, assuming the pollution is conserved, that there's none other produced inside or destroyed, then you can have a net flow of pollution out the box because there's a point source inside my volume. But if there were no sources on the inside, then there can be no net flux on the outside. There might be pollution produced elsewhere flowing in one side, but unless it's being created or destroyed in the interior, the same amount will have to flow out the other sides. if the thing is conserved. Okay, so that's the theorem of Gauss.